So now we know that they are perpendicular. The magnitude, the amplitudes are perpendicular to propagation. So for a given propagation direction n, we can actually define a coordinate system. So this E sub 1 and E sub 2, they are perpendicular to n, but we can also express the propagation in terms of fixed unit vectors. So if we define a coordinate system, coordinate system is epsilon 1, epsilon 2, both are unit vector, and the epsilon 1 cos epsilon 2 to be n. So they are all perpendicular to each other. So they form a local Cartesian coordinate system with one of the direction, one of the unit vector along n direction. And then we can express the what we call the polarization or the magnitude of the electric field express that in this unit vector. And we define that because later on we use that to analyze different kinds of polarization. Okay, so we start from this. This is given that the figure in 7.1 may be better than my picture, so look at that. So basically now we are, these are general solutions, but now we restrict to a particular solution along a given direction of epsilon, either epsilon 1 or epsilon 2. Okay. So like the electric field, I think Jackson start with epsilon 1. Electric field is around epsilon 1, right? And then you have the actually this is could be the magnitude, the amplitude of the wave is epsilon 1, and then by the equation that we just divide 7.11, so B would be, this could be this, you have this square root of mu epsilon vector, and they will be in the epsilon 2 direction. Epsilon 2. And with the same E sub 0, right? Because this is given by n cos E, this is given n cos epsilon 1 of epsilon 2. Right? So that this form one solution. They have to be related to each other like that. Another solution would be if the magnitude is in the epsilon 2 direction, then epsilon 2 now n cos epsilon 2 obviously is minus epsilon 1. This will be minus same magnitude. Okay, so that those equations 7.12 or 12 pi, right? That also straightforward. Now we talk about the energy of the wave. First, the pointing vector. The pointing vector S is for single frequency wave. We talk about that. This equals H, right? And because here it's depends on the product of two oscillator with the same frequency, and so we introduce a 1.5 factor, and then put a complex conjugate on one of the injects and use on H. H is just B dot B divided by mu. Right? And so now that is quite trivial. So you apply either one of them. Say if for this one And then again, assuming that these coordinate systems are real vector, we don't have this complex vector. We take complex conjugate of this one. It's just d over mu, and then take complex conjugate of just the e sub 0. Just e sub 0 is complex. And so that comes in 1/2 e sub 0, and then complex conjugate e sub 0 is e sub 0 complex magnitude square, right? And e sub epsilon 1 cos is epsilon 2 is in the n direction, obviously. This cos that is back to the n direction. And the other coefficients are this square root of epsilon over mu, because h is b divided by mu. And then all the corresponding to the n direction. Okay, so that shows that energy is propagating in the direction of the wave. N is the direction of the wave, but energy doesn't have to be propagated in the same direction. But for electromagnetic wave, at least in this simple situation, energy is propagating in the same direction. It's the propagation direction of the wave. Okay, so that's nice. So that would be 7.13. Right, that's for the first one, but for the second one, you can also work out exactly the same, because now it's E is epsilon 2 cos into epsilon 1 is minus n, but then you have a minus n. So either one of them individually satisfy the same relation at the Poynting vector for both of them in the n direction, because we have already chosen one solution. We are not consider this backward one. If you change the sign like the k vector, then one of these b would need to change sign also to give you the backward direction. Okay, and so that's Poynting vector, and then the same treatment you can apply it on the energy density. U is again it's also a product this electromagnetic energy density. So you have originally you have 1/2 of E dot H and then H dot B, right? You remember that the expression of the electromagnetic energy density we divided chapter 6 now becomes 1/4, because you already have this 1/2 factor, so it becomes 1/4. And you have two terms. One is E dot D, the other is B dot H. So E dot D is epsilon E, so you have dot one of them changed the complex conjugate, and then you have B dot H. So H is B over mu. B dot complex conjugate. Okay, so that not difficult. And then you apply to either one of these ways. For the first one, E is this one, and E complex conjugate. The phase we all cancel because all the phase has this E to the I. Right, for the propagating direction in N. So when you take the complex conjugate of the phase, that changes I to minus I, and the product will make it 1. So this phase doesn't contribute to this product. So only this one. So you have E dot E, this one dot into itself. So magnitude of E0 squared, just like this one. Epsilon magnitude of E0 squared. And likewise for B, for B here, so you have the square of this factor, so mu epsilon, but you divide it by mu, so you cover the epsilon, right? and then you have this e sub 2 dot into e sub 2 because the dot product, and again this take a compact conjugate become compact magnitude square. So basically, this term will recover exactly the same term, so you actually change it to 1/2. Both terms will give you the same density, energy density. Okay, so that is 7.40. Okay, so the physics is important actually. The energy in the electric field and energy in the magnetic field, they're actually the same. I mean, average, this is, remember this when you divide that, this is an average over the period of the wave. So this is the average electric field energy and average magnetic field energy are actually given by the same amount. So the physics is as the wave propagate, the electric field change the magnetic field, magnetic field change the electric field, and they are of equal amount. On average, they are of equal amount. Okay, and that is straightforward. And also, you now you see that from this S and U, then because both have the same E sub 0 square, magnitude square over 2. So you can say the S is equals to U. And then you have all these factors, but there are epsilon here, right? S is, so basically U divided by, so up to here is, it's just this one divided by, multiplied by epsilon is U. So you need to divide it by epsilon. And so you already have the square root of epsilon over mu, so divided by epsilon mu and U times N. Right. And this 1/2 square of epsilon mu is, we already defined that as your phase velocity. And this formula is given by this one. Energy density times the velocity. Especially in vacuum, that you can see is a P, is a C. Okay, so so far so good. It's almost done with section. The last one is this a discussion of the complex N. So far is all assume N is real. But for complex N is again a little bit strange. But let's use that so we can just follow him. N is you have this real vector as I times another real vector, right? You can do that. The relationship is still the same. N dot, now is the relationship become N dot N complex conjugate instead just another N. It's still like it's still 7.9. It's N dot N. This one is still this is still true, right? We still require that by because it's the Helmholtz law, Helmholtz equation. It says still satisfy the Helmholtz equations, and the N is 1. So and substitute this into here, so you have N R square and I N sub I dot into itself becomes minus I square. Right. NR, this NR is the magnitude of NI is the magnitude of NI. Then now the not necessary unit vector. These are not unit vector. Okay, so they satisfy this one. And the imaginary part is minus or plus 2i NR NI. That equals 1. Okay, so this is a complex equation. So in both the real part and the imaginary part has to satisfy the equation. So the real part of this equation is n all minus n squared equals 1. And the imaginary part is n all dot into n I 0. Okay. So again, to satisfy this, obviously, they cannot be 1 and n sub r and n sub I unless n sub I is 0. So that means go back to real situation. If n sub I is not 0, then n sub r is greater than 1. And another conclusion is these two parts is perpendicular to each other. So if n sub r is representing the propagating direction, n sub I is the direction when the magnitude change, then you can see that the magnitude can be either increase or decrease. When it decreases, like the wave is dissipating, and when it's positive, I mean, the other way is we can amplify along this n sub I direction. You can see that from the exponential factor that down here, so e to the I k. Now you can put the I inside this n factor. So you have I k n sub all dot x, and then the second part is your I times I is minus k n sub I dot into x. But obviously, you still have this time-dependent oscillation. But you can see that this two terms with the I in the argument of the exponential function is still just like what we had before. It's just these two represent a propagating wave, but this is just a pure real number. And so it means that the wave is exponentially decreasing in the n sub I direction, or in the negative n sub I direction, it's increasing. So it's represent a change of magnitude. Okay, so that is this, and one way to satisfy this two relationship is you define this just like the unit vector epsilon 1 and epsilon 2 use just use E1 and E2. They are perpendicular to each other, so you write n. And then to satisfy a real and satisfy this condition, you use a cos function. So E sub 1 unit vector or unit vector is cos theta plus E sinh theta. Now this is I. This is the imaginary part. This is the real part. Then the real part ends up all is this one. The magnitude is cosine theta because these are unit vector, real unit vector. So ends up all magnitude is here. So obviously cos square theta minus sin square theta. You know that's this one, right? No, this is elementary function, right? Then the second one is a trivial when we define E sub 1 and E sub 2, they are orthogonal unit vectors. So that is another way to write down this situation. But anyway, that's the end of section 1. So up to here is okay. All the math kind of straightforward.